Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today we're diving into a fascinating application of AI in computational science. Physics-informed neural networks, or PINNs, for solving partial differential equations. Exciting stuff.
Absolutely. I've been reading about this. The core idea seems to be using neural networks to approximate solutions to PDEs, right? But what makes PINNs different from just a regular neural network approach?
Precisely. The key is that PINNs aren't just blindly fitting data. They incorporate the underlying physics of the problem directly into the training process. We're not just approximating a function. We're approximating a solution that obeys known physical laws. Think of it like this. A regular neural network might learn to predict the trajectory of a ball, but a pin would learn that trajectory while also respecting gravity and air resistance.
That's a great analogy. So how does this incorporation of physics actually work? Is it just adding another term to the loss function?
Exactly. The loss function includes a term representing the residual of the PDE. For example, in the 2D heat equation, the residual is the difference between the time derivative of temperature and the Laplacian of temperature, scaled by thermal diffusivity. The network is trained to minimize this residual, ensuring the solution satisfies the equation.
I see. So the network learns to minimize the error in both the data and the physical law itself. That's clever. But what about the challenges of solving PDEs? The article mentions several, like limited data and high computational cost.
You're spot on. Traditional methods like finite difference or finite element methods can struggle with these issues, especially in higher dimensions. PINNs, however, offer some significant advantages. First, they can generalize well even with limited data, because the physics are baked in. Second, while the training process itself is computationally intensive, once trained, the PIN can provide solutions much faster than traditional methods for new inputs.
That's a huge win. So the article shows an implementation for the 2D heat equation. It's pretty straightforward, using standard neural network libraries like PyTorch. But the key is that physics-informed loss function, right? It uses automatic differentiation to calculate the derivatives needed for the heat equation residual.
Precisely. The beauty of it is that the automatic differentiation handles the complex calculations of partial derivatives, which are often a major hurdle in solving PDEs manually. The code is relatively concise, focusing on defining the network architecture, the loss function, and the training loop. The output, as shown in the animated GIF, is a visualization of the heat diffusion over time, demonstrating the accuracy of the PINN's solution.
One thing I found interesting, though, is that the article mentions other methods like FDM and FEM but doesn't delve into them. Maybe a future episode could compare and contrast these approaches more directly? It would be a great follow-up.
That's a great suggestion. A comparative analysis would definitely be valuable. It would allow us to highlight the strengths and weaknesses of each method more clearly. But for now, the key takeaway is that PINNs offer a powerful, flexible, and efficient way to solve PDEs, especially when data is scarce and physical consistency is paramount. They represent a significant advancement in computational science, bridging the gap between data-driven AI and physics-based modeling.
Absolutely. A really exciting development. Thanks for breaking this down for us.
My pleasure. And to our listeners, thanks for tuning in to Tech Bytes and News. We hope you found this discussion illuminating. Have a great day, and we'll see you next time.
Bye-bye.